Today I would like to talk about my topic, thesis title of Overtopping Wave Energy Device. So the presentation outline of my presentation today is introduction, literature review, research methodology, results discussion, recommendations, and conclusion. So basically, what is an overtopping wave energy device? Basically, it starts off with the wave overtop into the reservoir here via the ramp, and then the reservoir will act as a potential energy storage area, and the turbines inside will generate electricity, and after generating electricity, the seawater will be released back into the sea, and the process will go on and on again. So the problem statement of my thesis is there has been no overtopping wave energy devices so far developed in Malaysia, and Malaysia has low wave conditions, so it is quite important to improve the overtopping device. And what are the suitable characteristics for this overtopping wave energy device in Malaysia? And the objectives of my thesis is to develop a preliminary design for overtopping wave energy devices, as well as to perform an analysis on the ramp angle to determine the maximum overtopping rate. So a brief introduction. According to Flavin and O'Meara, as many as 2 billion people today elect electricity. So with this rapid population growth, the demand of electricity will definitely increase. The topic that I'm focusing on today is overtopping wave energy device. So it is part of the wave energy device, which is a part of renewable energy. So some literature review for my thesis. Basically, there are a few advantages of wave energy. It has number one, it has high power density. It is more predictable when compared to wind energy. And according to Thorpe, the potential of wave energy in the market is currently valued at 2,000 terawatt-hour per year. So as you can see from the figure, these are a few classification of wave energy devices. But today I'll just like to focus on my topic, which is overtopping wave energy devices. And currently there are these three big overtopping wave energy devices currently available in the market. The first one being Wave Dragon. As you can see from the figure, it has two patented reflectors, and it helps focus the waves onto the ramp. And this ramp here, it aids the overtopping process. And it also has a reservoir in the middle, and as well as low head Kaplan turbines, which operate at a very low head, about 0.4 to 4 meters, and also operate from a zero to full load condition very often. So second being Topchan. It is a shoreline overtopping wave energy device, and its prototype in Norway is rated at 350 kilowatts. It also consists of a reservoir, Kaplan turbine, and a narrowing channel. So the number three is Sea Wave Slope Con Generator, SSG. Its key features being it has multiple reservoirs and a multi-stage turbine, which is called MST. And the energy extracted is directly proportional to its elevation above the mean seawater level. So we have to take note of the wave conditions in Malaysia because we are designing some device according to our local sea conditions. So according to MMS and OMAR, the average significant wave height in Malaysia is 0.5 to 1.5 meters. The wave period being 4 to 8 seconds, and wave climate is 2.37 kilowatt per meter. So now I'd like to talk about my research methodology. Basically, I did some research on the overtopping devices available, and then I determined the location of the installation of the device, and then I came up with some initial design sketches, and I determined a final design concept. So from there, I did analysis on the ramp angle variation, using also several CFD tools like ISAP, Fluent, and CFD posts. And from this analysis, the maximum average overtopping rate is determined. So the location is Pulau Tinggi, which is about 20 nautical miles from Mersing. These are the few design parameters affecting the efficiency of my device. Basically, as you can see from the figure, the angle, the shape, guiding wall, the plate, crest freeboard, shape, and draft. But for my thesis, I'm only focusing on one analysis, which is the ramp and inclination angle analysis. So these are the way I use to determine my main dimensions for my device. Basically, the length and width of my device is scaled down from this actual prototype of Wave Dragon, and by a factor of 6. So the length and width are 50 and 28 meters respectively, and the angle of deflectors is 45 degrees, and design draft is 3 meters inclusive of the vertical plate which I designed below the ramp. Number 4 is the height of upper and lower reservoirs. So in order to cater for our local wave conditions, the height of the lower lower reservoir is 1 meter above mean water line. Higher one is 2.5 meters above water line. So the height of guides, according to experiments, these two heights actually help increase the overtopping rate, which is 3 and 1 meters respectively. And number 6 being maximum operational depth, it's 15 meters. And the height of the mooring system is 20 meters. And the mooring system that I use is this rack and pinion design, which is now currently used in jet couplings. So for the ramp angle variation, according to NUM 2008, the slope angles lies between 32 and 45 degrees to yield maximum overtopping rate. And according to Dos Santos 2013, the optimum ramp angle is 30.96 degrees. Hence, the angles I've chosen for my thesis are 25, 30, 35, and 40 degrees. So these are the tools I use for my design concept and my analysis. So I started with AutoCAD for 3D drawing for the design concept and 2D drawing for the ramp angle variation. So the 2D drawing focuses on the energy collection area, which consists of the ramp, the lower reservoir, and the entrance to the upper reservoir. And ISAM is used for grids generation. Basically, it helps to build point surfaces and boundaries. And it's also used for building a mesh for analysis and extrusion of symmetry. Next is Fluent. It basically helps to read meshes from ISAM, and as well as perform CFD calculations for the analysis. And prior to the running the calculation, the setup of the problem has to be checked. So basically, these few problems have to be determined. The materials, the boundary condition of the velocity inlet, it has to be make sure it's intermediate waves from the wave input parameters. And the solution is initialized from in water, which is where the waves enter the domain. And the period of calculation has been determined to be 50 seconds, and each time step is 0.1 second. So we need like 500 time steps in order to cover the period. And lastly, it's CFD post. I use CFD post to analyze the results of the calculations from Fluent, and I use it to observe the wave simulation to see how the waves react when it's in contact with the overtopping device. So I basically have to create an ISO surface and an ISO clip to determine if the wave overtopped into the reservoir at a particular time step, and to monitor the water volume fraction. So to determine the overtopping rate, I use the continuity equation, which is Q equals to AV, whereby A is area and V is velocity passing through the reservoirs. So this A and V can be determined through the function calculator in CFD post. And from the dispersion relation, which is omega squared equals to GK, hyperbolic tangent HKD, I made these two equations can be determined, wave velocity and wavelength. And from these equations, for a period of 6 seconds, which is according to our local wave conditions, the wavelength, wave number, and wave velocity are determined. So in order to determine this average overtopping rate, I have to determine the area under the curve, which is shown in this figure here. And the first Simpson's rule is used to determine this area under the curve. And average overtopping rate is determined according to these equations here. So these are my results, and I start off with the initial design concepts. So my design concept 1, 2, 3, and 4. So from this, I incorporated the advantages of everything, and I came up with the final design concept. This is the front view, plan view, and isometric view of the device. So these are some renderings that I did for my concept. And these are the main dimensions as determined earlier in the methodology section. So these are the graphs that I've plotted from the analysis. Basically, it's a graph for every ramp angle at its upper and lower reservoir. So from each graph, I can determine the average overtopping rate from as determined earlier. So it is 25 degrees upper, lower reservoir, 30 degrees upper reservoir, lower reservoir, 35 degrees upper and lower reservoir, and finally 40 degrees upper and lower reservoir. So from this analysis, the average overtopping rate for highest of the average overtopping rate for the upper reservoir is for the ramp angle 30 degrees at a rate of 3.673 meter cube per second. And for the highest of average overtopping rate for the lower reservoir is for a ramp angle 40 degrees at 3.725 meter cube per second. So the discussion from my thesis is that the overtopping rate is for the lower one is higher than that of the upper one because the waves will overtop into the lower reservoir first before overtopping to the upper reservoir. And the analysis done in 2D because due to limited computational resources. And for the recommendations for future work, basically a longer period of time is needed for the CFD analysis. And then the simulation should be done in 2D rather than in 3D. I mean in 3D rather than in 2D. And the ramp shape can be varied. Because based on literature reviews, it says that a weak convex ramp shape can boost the overtopping rate. And lastly, the wave parameters can be varied according to Malaysia's wave conditions. So the conclusion of my thesis is that preliminary design of an overtopping wave energy device has been developed. And the average overtopping rate Q is highest for 30 degrees for the lower reservoir, and highest for the upper reservoir is the ramp angle 40 degrees. That's all for my thesis presentation. These are the references I've used for my thesis. Thank you.
Thank you. Questions from panel?
Okay, I want to see your design.
The final one.
Yeah, the final. Good. Okay, use a mouse so I can show you. Where is the water level?
Basically somewhere here. The mean seawater level is here. So at a lower wave height, you will overtop in the lower reservoir, and higher wave heights, or basically about 1.5 meters, you will overtop in the higher reservoir here.
The lower reservoir is what is the height of that? Lower
1 meter above mean seawater level.
1 meter.
What is the wave height?
Within the range of 0.5 to 1.5 meters.
Which is possible to go into the first level of reservoir like that. Which is not in the-
Yeah, but basically the 1.5 meters can sometimes be overtopped into the higher reservoir, based on my analysis.
This your design is a fixed time or is a floating free floating time?
It's actually, as I said earlier, it's moored by the track uplink
So
system.
it's a fixed time.
So it is more to that this area here. So it can move up and down based on the wave conditions. And also actually based
level, right? Not wave condition.
because if there's very strong waves or it's too strong, like during, let's say if there's a tsunami or something, it can be raised higher so that it won't damage the hull.
When you know there's a tsunami, you have come to the place up.
I mean, if there are strong, if not tsunami, there are stronger wave conditions, and it's too, the hull cannot take the strength.
So water goes into the reservoir, then
It'll overtop into the reservoir.
it needs to flow out, right?
Yeah.
Flow to the bottom.
Yeah. Basically, because for my design, I'm actually focusing on the energy collection area. Because the turbines, everything will be designed by someone else. So this is actually a rough design concept for me. So it's not the final design concept which they're going to use.
What is, okay, you mentioned about Wave Dragon. Basically, I see this is like a copy of the design of Wave Dragon, right? So how much different is the design from the Wave Dragon?
For Wave Dragon, they only have that two reflectors and the ramp. Basically, that's all. And I incorporated a few design concepts like Upshot, this wave guide thing. It's actually similar to the narrowing channel, which will help increase the overtopping rate. And this lower reservoir ramp, it caters for local wave conditions. Whereas Wave Dragon is really catered for like European wave conditions, which are really high, like 3 meters and above. So
Your
we
ramp
have
is similar to your ramp, right? This is with an angle. Your ramp.
which one? Wave Dragon? Yeah, it's with an angle, but basically it only has one reservoir. It has to overtop from the ramp into the reservoir. So, but for us, because we are designing this wave overtopping device, if our reservoir is, let's say, too high, the waves won't be able to overtop. So that's the problem that we face here.
Why don't you make the ramp with 1 meter high?
Because if it's too low, and then there won't be much potential energy to harness from. Because the energy extracted is directly proportional to the elevation from the seawater level. So if it's too low, then there's no point in having the device.
Then
That's why
what is the meaning of what is the point of having a 1 meter ramp there?
so that we can harness the lower wave heights,
But you say that
as well as to harness the higher wave heights. We cater to two conditions from here, within the range of the local.
Imagine when the wave comes in, right?
Yeah.
Okay, there is energy in the wave, okay, and when you have the first ramp, okay,
Yeah.
the energy is being absorbed into the first ramp.
Yeah.
Okay, the energy of the wave might not be enough to reach the second ramp. So basically, you
So
are
that's why
still
if you
taking
don't
up.
have a ramp there, basically I would say less waves will be overtopped into the upper reservoir. So those waves, if they cannot go up to the reservoir, you can go into the lower reservoir. You can still go into the lower reservoir, and from there you can harness the energy.
Well, okay, let's say now you mentioned about the wave height is 0.5 to 1.5 meter, right?
Yes.
Okay, so basically wave is below 1 meter, you won't get the energy, right? You won't get the
You mean the wave height or
wave height.
basically 0.5 meter? It's still possible for it to go in.
Yours is only yours is 1 meter high.
The lower reservoir, yeah, it's 1 meter high.
Yeah, then how can the wave go in?
The 0.5, because sometimes there will be, it's not only 0.5, sometimes there will be in between 0.75, because it's wave, it's not stagnant, it's not calm.
Also,
Because from my analysis I've done in CFD, using CFD tools, the waves can overtop, no problem. Because from my analysis I'm actually using an average, because the wave period is from 4 to 8 seconds, I'm using 6 seconds as an average. And from there, I determine the wavelength, the wave input parameters, basically the wavelength, wave velocity, and wave number. So that's why in my recommendations for future work, they can actually vary these wave parameters, like if they change the period and stuff. But it has to cater to the local wave conditions.
so in the design you have two reservoirs or just
Two
one?
reservoirs.
So the first 1 meter reservoir will be different. Is a different type from like that wave that water down or water.
Basically, I haven't really done any design for the internal part because I was told to focus for this RAM energy collection area, basically to determine which RAM angle will yield the highest overtopping rate, so that in future work they can use this RAM angle, which is the best RAM angle to yield the highest overtopping rate. So they'll incorporate my design for this RAM angle into PR design.
Ramp angle.
Yes.
What's the angle?
That's why in my conclusion I have two for lower and upper reservoirs. The highest overtopping rate for an upper reservoir is 30 by the RAM angle 30 degrees, and the lower one is 40 degrees.
How many tests?
I ran the analysis for a period of 50 seconds.
From what angle to what?
I basically did every single angle, 25, 30 degrees, 35, and 40
Starting
degrees,
from?
25.
Starting from 25.
based on the literature reviews, because most of the literature reviews, as you can see, it gives about 30 degrees and above.
Until what angle?
40 degrees, 25 to 40. Four angles.
5 to 4 degrees. And increment of every 5 degrees. 5 degrees.
Basically, the literature review, I use that in those angles as a range.
And then the wave height that you use estimation?
Wave height is because I determined my wave height from here. Because in the analysis, I think the wave height wasn't required to be in the CFD to influence. Basically, they needed the wavelength, wave number, and the wave velocity from calculated from this wave period.
What is the wave height that you use? For these numbers, and what is the wave height that is being generated?
0. I think it was 1 meter. The average between 0.5 and 1.5 percent.
So you vary.
That's why, because in this analysis there are so many parameters that you can vary, like this wave parameters. You can even vary the ramp shape, ramp angle. So for my thesis, I only had the time to do the ramp angle variation analysis.
So you fix with one wave parameter.
Yes, basically that's it. I take the average within the range. Just from this experiment itself, it already took up a lot of time.
How much time do you need for one simulation?
One simulation, maybe a few hours.
Any correlation on the relationship between this ramp angle and wave characteristic?
Wave characteristics and ramp angle.
Let's say wave height or wave slope angle.
Yeah.
You see any relationship between this ramp angle and wave and whatever wave characteristic? Which one is varies? Let's say you chose you do various ramp angle, yeah?
Yes.
So how about the
I fixed the wave parameter. That's why I was telling Dr. Koro this now. Because if you fix, I vary the ramp angles, but I fix the wave parameter. Yeah. So from there I can know like which ramp angle use the highest overtopping rate. So that's why in my recommendations for future work, they can try to vary. Since I've already have a guideline for which ramp angle will yield the highest of the overtopping rate, they can then vary the wave parameters from there. Because I fixed that one parameter as an average for the local wave conditions.
which one better when this wave, let's say wave ratio or ramp,
Yeah.
break there, or you must make the wave, it doesn't break, it go through which one better, you like?
Because basically now I have two reservoirs. You can overtop into the either the lower.
I can't see what is the reservoir?
Okay.
Two reservoir.
Yes, lower and upper.
Lower, upper.
Basically, you can see from this figure, there's this lower reservoir which the waves can overtop into, and the higher one is here. As you can see from the plan view, this one is the lower reservoir. So the waves can the lower waves can overtop into here, this lower one, or the higher one here.
So where is the turbine? The turbine.
The turbine, it will be somewhere inside here. Because basically for my design, I'm focusing on this energy collection area, this part, the ramp angle. That's for my thesis.
What's the angle that the ref can use? I mean, brand, right?
Yeah.
Is it a new one?
It was used by this device called SSG, as I explained earlier. Basically, they had multiple reservoirs connected or electricity generated by this multi-stage turbine. It's connected to a common shaft. So basically, the turbine area is not my field of study here.
Then how about the angle? The one that you say SSG?
SSG. It's not mentioned in the literature here. Because
Where do you think the turbine is going to be located?
somewhere here.
Somewhere there.
Yes. It's actually someone else will be doing the analysis of the turbine. Actually, Shafiq is the one who.
When the ram angle is 30 degrees,
Yes.
the speed
Overtopping rate.
our speed is 3.67.
The rate, volume, flow rate.
Our volume.
Yes.
Okay.
Volume.
So when it is 40 degrees, it's going to be more, isn't it?
Yeah. For the lower one, because the 40 degrees one use higher overtopping rate for the lower one. 30 degrees use higher overtopping rate for the upper one.
Okay. Right. Any more question? No more. All right. Thank you very much.
Okay, I want to ask, are you going to continue with your study?
Masters, PhD. Dr. Ko is willing to provide you.